In this lesson, we begin discussing the trigonometric functions. This will be roughly equivalent to section 3.3 of our textbook, but we intend to go a little bit deeper because we are going to include the chain rule as well. Let's review the derivative rules and everything we learned so far. The definition of the derivative. This is the Newton quotient, which corresponds to the slope of the secant line. Taking the limit, we get the slope of the tangent line, and then changing x values around, we get a new function given by the slope of tangent lines, and that's a derivative function. Derivative rule for constant, sum, and coefficient are here. Power function, exponential functions, and logarithmic functions are here too. We have the product rule, quotient rule, and the chain rule. Inverse function is something we're going to discuss a bit later. Now let's talk about the limit computation for trigonometric functions. This one is really fundamental limit identity for trigonometric functions. Limit as theta goes to 0, sine of theta with theta is 1. This is rather difficult to prove, so I kind of buried it to the appendix as a matter of fact, in that I'm going to prove this formula along with a lot of other differentiation formulae. This one, on the other hand, we can handle it. We're going to use this one and some trigonometric identities to prove it, and here we go. Alright, we just begin by multiplying by conjugate cosine of theta plus 1 to both numerator and denominator. Because I'm multiplying the same thing to both numerator and denominator, it's essentially multiplying by 1, so there's nothing changed. However, the numerator becomes a minus b times a plus b form, so a squared minus b squared, we get cosine squared minus 1 squared. But what is that? That's negative sine squared because of the Pythagorean identity. Now, we have sine and then we have just theta down here, so we can decompose the numerator into sine of theta over theta, and then sine of theta over cosine of theta plus 1. What does the first fundamental identity say? Sine of theta over theta goes to 1, so this limit is going to 1. We have this negative sign before, and then this one is the trivial limit actually. Sine of 0 over cosine of 0 plus 1. So that's 0 over 1 plus 1, that's 0. So negative 1 times 0, we're going to have 0. What we are going to do in these problems is basically replicate what we did. Embed sine of theta over theta somewhere and then do the computation, kind of like these. But this was harder because we had to use Pythagorean identity. These problems will be much easier actually. How about the first one? Sine of 7x, if we have 7x down here, it will go to 1. Sine of 5x, so I'm going to need 5x down here. So how do I manipulate? 7 times 5 to both numerator and denominator. And then what? Sine of 7x over 7x, that's going to go down to 1, as highlighted in blue. And sine of 5x over 5x, that's going to go down to 1 as well, as highlighted in red. Consequently, I have 7 times 5, that's 35. Those blue and red parts are actually application of this one. We have to use the same angle theta. How about the next problem? That's even easier. All I have to do is recognize that cotangent is cosine of a sine, and what do I have? We have x over sine of x. The same situation. This limit is going down to 1. How about the next problem? Well, we can factor the denominator, and then what do you have? Sine of x minus 1 over x minus 1. And that's going to go down to 1. Again, from the same identity. So what do we have? 1 times a trivial limit. Plug in x equals to 1, I'm going to get 1 times 1/4. The next problem, well, this may be a trick question because this is the only one problem among here that have nothing to do with this one actually. But actually it's easy. All I have to do is recognize the tangent is sine over cosine, and then what we have, taking the common denominator, we get cosine minus sine in numerator. Denominator is sine minus cosine, so we have obvious simplification. We end up with this trivial limit. By plugging in, we get negative square root of 2. Well, that was the limit computation, and there's no need to pay too much attention to these, so let's move on to the derivative computations. Here are the derivative formulae. Derivative of sine is cosine, derivative of cosine is negative sine. Again, I'm not going to make any attempt to prove these, and I'm going to do that in the appendix. The others, well, actually we can do that. It's a little bit difficult, but we can handle it if we be careful. So let's calculate the derivative of tangent function, and what we need to do is to recognize that tangent function is actually sine over cosine. Consequently, we can apply the quotient rule. So what do we have? Denominator will be cosine squared. How about the numerator? Derivative of numerator u prime is going to become cosine of x times denominator, just cosine of x, just copy it, minus numerator sine of x times derivative of denominator, negative sine of x. So what do we have? Because these two negative signs cancel each other, I have cosine squared sine squared x divided by cosine squared of x. And of course, everybody remembers what is cosine squared plus sine squared. That's going to be just 1. So this is 1 over cosine of x, total quantity squared, and that is secant of x, secant squared of x. So we can deduce this formula using these two and the quotient rule. We can do the same thing to the other formulae as well. Cotangent is cosine of a sine, so again you use the quotient rule and some manipulation. Secant is 1 over cosine, so again quotient rule and some manipulation. Cosecant is 1 over sine, so again the same story, quotient rule and then some manipulation. We're going to get these formulae. I'll leave the details to the students because we demonstrated that this is certainly possible. Okay, next we're going to move on to some applications of these, and then let's do some computation. How about the first problem? Looks like this is going to be a product rule problem. First function and then the second function, and looks like the second function is going to be a logarithmic and tangent. Okay, it has some trick at least. And then here it is, changing back into power form and then some simplification. Alright, and then the derivative of numerator is here, u prime, and then v, just copy it, plus u, just copy it, and v prime, that's a derivative computation again, logarithmic function, and a tangent becoming secant squared. Elementary. How about the next problem? Looks like you'll have to use straight ahead quotient rule computation, so I'll just leave that to the students. Next one, C, will be a little bit more challenging because we have to use quotient rule, of course. However, pay particular attention to this part, y squared times cosine of y. When you do the derivative of denominator, you'll have to consider this part as well, and that's going to be the product rule. What am I talking about? Right here. This is it, u over v, and then I highlighted that product part in red. So here we go, u prime v minus uv prime. When you calculate this v prime part, sine becomes cosine, good, but here is the product rule, so we have to use the product rule again. Quotient rule and then product rule. How about the next problem? This is going to be a quotient rule again, of course. We have this outer structure is numerator, denominator, so that's quotient rule. But inside the numerator, we have sine of something, so that's going to be a composite function, so it's a chain rule. Here's another composite function, so we need another chain rule here. Let's open up and let's discuss this one. Here I highlighted these as blue and red respectively. Wait a minute, I made a little mistake here. This should have been cosine. And then I am losing that font color. Okay, finally corrected. Alright. And then looks like we'll have to correct this one. We're gonna do that. This is u over v, so let's apply the quotient rule. U prime v minus uv prime. So when you calculate u prime, then this derivative is just fine, but for this part you'll have to apply the chain rule. Sine function becomes cosine function. Nothing changes inside, and then we just multiply the derivative of the inside, 2y plus 2. How about the next part? Well, let's see. Obviously, I changed my mind from cosine function to logarithmic function. So we have this log function showing up here. Sorry about that. Okay, I think we covered everything now so far. Okay, so u prime v, so nothing changes here, and this is u, so nothing changes here, and then here we go with v prime. The first function, this 2y, becomes 2. That's okay. And then the derivative of this cosine function, okay, that's going to be a problem. Let's redo that. Derivative of cosine is negative sign. Colliding with negative sign already, I'm going to get positive sign. And then nothing changes inside, right? Y squared plus 1. And then finally, we have to multiply the derivative of the inside. That's 2y. And let me highlight this part in red to represent that this came from this composite function. And now this completes the solution, I think. Okay, there are a couple more problems. Okay, and then we have some time left, so let's talk about these. How about problem E? Sine squared x cubed plus 2x. At first glance, it looks like the outermost function is sine function. However, that is not the case. The outermost function is actually a square function. Sine function is the next inside, and then we have x cubed plus 2x inside. And this kind of notation, square all the way outside is becoming sine squared, or sometimes sine cubed and so on, is really a bad abuse of notation. But I'm afraid that kind of thing was invented far before any of us was born, so we are stuck with this. And you have to be careful about that. So let's use the chain rule. 2 comes out, inside stays the same, and 1 power, so I don't have to do anything because it's first power. And then the derivative of next inside function, sine becomes cosine. And then, using the chain rule again, the derivative of the inside, 3x plus 2. Tricky, but here it is. Make sure whenever you have sine squared or cosine squared or tangent to the third power or something like that, it's going to be the power function all the way out. Remember that, please. Couple of problems left, but I'm going to leave the other two to the students. More derivative problems, or combining the derivative technique with tangent line problems. We have done that many times, so I'll leave that to students.